So still on worksheet 2B, we have one last application. It has some data written in a chart that tells you the population of Miami-Dade County, and it does tell you it's growing exponentially. So it gives you 2 data points, which frankly is not enough to do any statistical analysis, but whatever. So it starts in the year 1990, and then they have another data point collection a decade later at the year 2000. So population at the, quote, beginning of this problem is 1.94 million, and then at the next data point, it's 2.25. And they want you to set up an exponential function in order to find the rate. So the exponential function that you guys are familiar with is this guy. But it's going to be kind of backwards to what you guys are used to because we don't know the rate that it's increasing by. So we're going to have to set up what we do know, leave rate as a variable, and then come back and find r, and then we can go set up the function. So the y value is an ending amount or a final amount of your population. So for this very small story problem, this number of 2.25 million is the final amount of the population for this question. So that's going to go right here. And then the a, the number in front of the parentheses represents the initial amount of the population. So at the beginning of this story, you initially started with 1.94 million. 1 plus, you are not going to know the rate. But to go from beginning to end of our problem, we do know how much time elapsed. How many years went by here? 10 years. Very good. So if I think about how I'm going to algebraically solve for r, you're going to start by dividing both sides by 1.94. And right off the bat, you're going to have some gross decimals. And we're just going to have to kind of suffer with the math and write out the gross decimals. So 2.25 divided by 1.94. I'm going to write my work over here. Is it like 1.1598? Okay. And it still equals the quantity 1 plus r raised to the 10th power. So 10th power is not a common power. We need to undo the 10th power. You can 10th root the equation. But for me, I don't like to use the x root key. It just bothers me. So if you don't want to use the x root key, you could just raise it to the 1/10th power. But you guys are welcome to go to the math menu and use the x root and just put a 10 into the index. That would work as well. Either way, you got to raise this up to a power or take the 10th root of it, and you get, is it 1.01494? 1.01494. But remember, we still have the quantity 1 plus r. So obviously your last step is going to be to subtract the 1 from both sides. And you find out that your r is 0.0, let's just round to 0.015. So identify the rate of growth and then go back and write an exponential function. So for part A, they're going to want you to go back and leave y and x or t or whatever as variables right now, but do plug in the initial amount. So the population started at 1.94. It's growing at a rate of 1.5%, which you still have to write as 0.015. And then leave it up to the x power, or you could say t power, any variable you want. So for part B, they want to know when your model, use your model to predict when the population is going to exceed 2.7 million. So back in Algebra 2, you guys would type this function into y1, and then you'd go to your table, and you'd kind of scan down the table to see when it elapsed past 2.7. And then you'd use that information to give an estimated answer. But you're in PreCalc. You're better than that. So we're going to have to get more accurate answers here in the future, so why not start talking about more accurate answers right now? Here's what we're going to do, guys. You're going to enter this into y1, and then into y2, you're going to enter your target. Your model wants to reach 2.7, right? So go ahead and get this function typed into y1, that function typed into y2. Ignore that. That's next week. What was it, 1.94? So we're going to have an exponential function simultaneously graphed with a horizontal line across at 2.7. So we're going to need to adjust our window, and we can do this manually, guys. X represents how much time has gone by since 1990. So 0 would be an appropriate start to time, and this is the year 2018. So that would be like 28 years later, so let's just go big and say 30 years. And then I hesitate to do zoom fit because I'm really kind of guessing on the x's to begin with. So think about this, guys. You just want to know where it crosses a line at 2.7. So your y's just need to surround 2.7. So go a little below and a little above 2.7. So like Lazy Abruzzo says, 2 to 3. And then when you hit graph, you should see an exponential curve, also followed by a linear, a horizontal line. There's the exponential. There's the line. And I can see where they intersect, which means my calculator can find the solution. So go to Calc. We're choosing intersect because I want to know where they cross. And then I like the intersect one because you just have to enter 3 times. Enter, enter, enter. So an answer of 22.2 years would be good, but there's a better answer. Because when did this model start? In 1990. Okay, so now that I think about this, this is a really stupid question. Because according to this model, the population for Miami-Dade County would reach 2.7 million in the year 2012. What year is it? It's 2018. What a dumb question. My bad. Maybe some more updated information, Abruzzo. All right, so here you found out that x was 22.2, but if your year started in 1990, that would be 1990 plus 22.2 years, so after 2012. Now, the other point that you're going to bring up when you guys take a statistics course, that was purely based on the model, a model that only had 2 data points. Do you think this is a good model? Because I really doubt it. I mean, math, you don't usually get 2 data points and then say, this is how all of Miami-Dade County will behave for the rest of time. Yeah, probably not. All right, moving along, guys. We already finished that, so that your homework should have been pretty much attempted. Tonight, yes, you have 2 assignments given to you, I noticed back there. So the rest of page 166 is given to you. It starts at like number 25, 26, 32, and 35. Those are very specifically, it's just the story problem part of our lesson from yesterday. So setting up like continuous growth, evaluating your functions on your calculator more than likely. And then the secondary assignment on page 178 that you're assigned today is going to be all in the logarithm properties that we're going to discuss next. So find worksheet 3. And you might want to get out your chart of squares, cubes, fourths, and fifths. So 3.1, yesterday's lesson, focused all on your exponential functions. 3.2 is going to focus all on your logarithmic functions. So look at your calculator, guys. Do you see the logarithm buttons? Let's start there. There's 2 of them. The first one's obvious. It says log. This guy. And what kind of log is that? Anyone remember? It is a base 10 logarithm, also known as a common logarithm. How do you know it's a base 10 logarithm? Because right above it on the calculator it says 10 to the x power. And then right underneath that is what? Natural log, which is ln. I blame the French still. And what is the base of a natural log? It's base e logarithm. So e is a number, it's just a weird number. And right above the natural log key, you guys see e to the x power. Your calculator is set up in inverse functions. Have you ever noticed that? So like tangent and inverse tangent. Sine and inverse sine, and same thing with cosine. Square roots and squares, they're all on the same button, and that's by design. They want you to understand where to find the inverse functions to each function. So knowing what we know about inverses, here is in black, this is the exponential growth function that we discovered yesterday. of some base that creates a growth, apparently. Now, inverses are reflections across the line y equals x. So if your growth function has a horizontal asymptote at y equals 0, knowing that he's the inverse function, it would make sense that this logarithm has a vertical asymptote at x equals 0. But here's the problem. Go to your calculator and type in, ignore the other functions, get rid of those. Just type in the common log of x. And then go back to the standard viewing window. So zoom 6 before you hit graph. Or just hit zoom 6. See any problems with that? I see a problem. So your calculator, as amazing as it is, it doesn't do a really great job at graphing logarithms. It makes it seem like the red, you guys might have blue, but mine's red right now. Oh, come on. Pen, work. Yep, it's going to do this to me today. Oh, for Pete's sake. Okay. So it makes it seem like the function stops right here, but in actuality what's happening is it's coming down and it creates a vertical asymptote along the x-axis there. Or sorry, the y-axis. X equals 0 line. So when you guys graph a logarithm for me on your upcoming homework, tomorrow's lesson, and then your test next week, I'm going to know who knows what a logarithm looks like right away, because you're going to have these weird little stumpy graphs that stop. And that tells me you don't know what a logarithm looks like, and you're just kind of going off your calculator. You have to be smarter than your calculator. Calculator's pixels only allow for so much space. So like when he goes to calculate the common log in between 0 and 1, it literally can only come up with like 1 point, and then it's like, I'm done. So there's a bunch of points there. They're just really, really tight on the y-axis. So it's not able to graph any more than this. So keep that in mind when you guys are graphing. We'll talk a lot about graphing tomorrow. I'm hoping to start it today, though. Let's talk about switching forms. So we have logarithmic form versus exponential form. And yes, you have to have it memorized. You must know how to convert between the forms. So there's a bunch of ways that teachers can write the form. But what I like to do is I like to write them with actual words. And this is the same way I do it in Algebra 2, and I just kind of stay with it. So I write the symbol for a logarithm, which is log. And then underneath that, you would write the base as a subscript. Now, not every teacher does this, but I like when you guys have parentheses around what is in the logarithm. So I've, very creative of me. I call this the number. I know, very creative, Abruzzo. Number. And then it equals, what do you think I called the thing that it equals? The answer. Clever, I know. So now this is logarithmic form. What we're going to do is we're going to transfer this logarithmic form to exponential form. So it starts with identifying who the base is. So we call that base. And he's holding up the exponent. The exponent is from the answer to the logarithm form. So the answer is what goes up here. And his solution is actually the number that's in the logarithm. Remember that transferring formula? So this is called exponential form. Your brain only works in exponential form. Your brain does not understand logarithms unless for some reason your brain has memorized all the logarithmic functions. I hope not. That's weird. So like log base 2 of 7, you should not know what that is at all. You might be able to estimate it once you transfer it to exponential form. So that's the importance of knowing how to go between the forms, is because when you have to do something without a calculator, which there are many times that will happen to you, and also speed is of the essence, you're going to have to be able to evaluate these without a calculator at some very near future point here, guys. So I've already had multiple people say, Abruzzo, I'm just going to use the change of base formula on my calculator, and I'm going to go, okay. You won't enjoy your score. So you have to know how to do these by hand, guys, without a calculator. Long-term goal, guys, remember the no calculator part of your SAT test? Yeah, this is one of the skills that they're going to expect you to know. Plus, knowing how to transfer between the forms is really integral to when we go to solve logarithmic and exponential equations. So we need these skills to build up on. So let's look at these examples here, which are in your notes. Yes, all right, this one's in your notes. So you're just rewriting from log form to exponential form. So first, what I do is I say, identify the base. Who's the base? 14. Write it down. He's now the base of the exponential. Now in Algebra 2, I just used to always tell my kids, if you confuse the order, just remember, once you identify the base, the other two things just flip-flop order. So base raised to the answer. Who is the answer? Y. I'm trying to get my colors straight. All right, I used red. And it's going to equal the number that was originally in the logarithm, which was x. Very good. So that is going from logarithmic to exponential form. So same thing here for number 2. Who's your base? 17. He's now going to be raised to the, flip these around, what power? The second power. And it equals 289. Now that one's kind of nice because that should make sense, guys. 17 to the second power is 289. So if they're strictly numerical evaluations or rewrites, then you should be able to kind of double check with math. Like, yeah, that is right. When it's variables, you won't be able to check it. A couple of picky notational things since we're in PreCalc. I get this a lot in Algebra 2. Kids will write down, and then they're telling me that that says 14 to the y power equals x, when in actuality, what does it say? 14y, which is not the same thing, is it? So I'm going to be really picky with you guys about exponents being superscript and small, and also bases, in the next question, bases for logarithms being subscript and small. And those of you who are like, oh, but I have bad handwriting, you'll have to work on it, okay? So number 3, I have exponentials right now. I'm going to logarithmic form. So I don't really like this direction of the pattern, I think because I have to remember to write down log. So I write down the symbol for logarithm, but what type of logarithm is it? What is the base to this problem? A is the base, yeah. The thing that holds the exponent up in the exponent problem is also the base of the logarithm. So it's log base A. And then same thing with the other formula, guys. The next two items are just going to kind of flip-flop order. So log base A of what's in the logarithm? B. And what is the answer? It equals 20. Very good. I don't know why. I just really hate going from exponential to log. So usually what I do is I do a double check and put it back into exponential. Because I don't trust myself. All right, number 4. Going to log form. So what kind of logarithm is it? Log base 7, I heard. Thank you. So make sure that's a tiny subscript. And then what is in the logarithm? 1 over 343. Very good. And equals what answer? -3. Okay. There we go. Moving along. So these are the properties that are not in your notes, but they are in your book. And this is the time in your math life where you want to like not just go, oh look, properties, but like actually start to understand what this property is saying. So it says for a logarithm of base b of 1 equals 0. That's supposed to make sense to you somehow. But we just got done saying your brain doesn't think in logarithms, but your brain totally thinks in exponential functions. So can you do a quick rewrite for me? Rewrite this in exponential form. Who's your base? B. And apparently, if you raise it to the 0 power, you should get an answer of 1. Guys, stop and think about that. Anything raised to the 0 power, what does it give you? 1. So that's why this property makes sense. Log form doesn't really make sense. Exponential form, total sense. All right, look at this one. Again, log form, I don't really understand it. But if I rewrite it, it says b to the first power gets you b again. Yep, that's exactly how exponents work. If you raise something to the first power, you just get that number back again. So apparently these logarithm properties, if written in exponential form, make lots of sense. So then at some point we have to kind of just accept the logarithm properties for what they are. Now here's what I would like you to notice. Log base b of b to the x power equals x. So b to the x power equals b to the x power. True statement? True statement. All right, here's what's kind of cool. If these are true statements, that tells me that if you apply a logarithm of any base to an exponential of the same base, these knock out. Because they're inverse functions. Don't inverse functions undo each other? So the log base b and exponential base b knock out. There's nobody holding the x up anymore, so you end up with the x just dropping down. That's the inverse property of logarithms that we're going to use a lot. And this is the opposite of that. This is the inverse property of when you have an exponential with a power that is a logarithm of the same base. So again, b to the log base b, these are going to knock out. The x is just going to drop down, and you get x. So let's look at, before we get to examples, a couple of notational things. You guys already hit on this, but when you just see log of x, you guys told me that was the common logarithm, commonly used in math. So they were like, hey, let's give this an abbreviation because I'm sick of writing all this down. So they went with log to be the abbreviation for a function of logarithm. And then they said if it's a base 10 logarithm, which is apparently we're going to call the common logarithm, you no longer even have to write a base in the subscript. You can just say log. So whenever it just says log, you're supposed to assume it's base 10. It's nothing wrong. There is nothing wrong. If you wrote log base 10 of x, it's fine. It's just unnecessary. What is the base of a natural logarithm? I heard base e. So this is a really picky Abruzzo thing, and I don't know if I'm being mean about this, but I let it go in Algebra 2 because I'm just so happy they write ln instead of in that I don't really care what they write down. But in PreCalc, you guys know it's ln because it's natural log. So if you wrote natural log of x, that's great. You guys just told me it's base e, right? So I get this from Algebra 2 kids a lot. That's wrong. Isn't that weird? So that's actually nonsense is what they just wrote down. When a logarithm is base e, it is written like this. So this one's okay, and this one's okay. This is not okay. This is like double base e. I don't even know what it means. So just, it's a notational thing that like in the grand scheme of things, guys, I'm not going to like mark you down on your test for it. I just don't want you to move on to calculus and then keep writing things like natural log base e like that. That's weird. So common log has just log. Log base e means natural log. Natural log with an e underneath it is gibberish. Don't write it. All right, here we go. This is not on your paper? No. All right, help me. These are on your paper. Here we go. Without a calculator, guys, okay? No calculator, but you can look at your chart if you need it. This is log form. I don't really understand log form. My brain does not work that way. So first thing I'd like you to do, and this is the way it looks on your test too, I ask you to rewrite it. So rewrite it in a more brain-friendly form. So here's what's going on, guys. I want to know what this equals. So 5 raised to, now they don't tell you the power. They don't tell you the answer. That's what you're looking for. So what I have you guys do is put a question mark there. A little friendlier than an X, I guess. So 5 to what power is going to change this to a 1 over 25? That's the question. So then you think. How do you take a 5 and change it to a fraction? It's going to have to be negative. So that'll take it to a fraction. Now how do you take a 5 and change it to a 25? You make it a negative 2. So that'll take a 5 and throw it to the denominator, and it'll also square it. So that'll make it a 1 over 25. Here we go. Make this in a more brain-friendly notation because this is not it. So 3 raised to some mystery power is supposed to give you the square root of 3. Okay, I got many problems with this problem. First of all, square root of 3, I don't like that notation either. What's a power way of saying the square root of 3? 3 to the what power? Is it that 1/2 power? That's the same thing as square root? Well, guys, this is no longer a really tricky question because look at it. It says 3 to what power equals 3 to the 1/2 power. Methinks the power is 1/2. See it? So the answer here is 1/2. This is still on your paper, I believe. Okay, so here, you don't have to rewrite it because I want you to use the inverse properties. If you have a logarithm and an exponential base that are going to knock each other out, Show me that. So natural log of e to the 7th power. Natural log and e are inverse functions to each other. They knock each other out. The 7 no longer has anything holding it up, so it just drops down. Your answer is 7. E to the natural log power of 5. E to the natural log, those functions will cancel each other out. The 5 drops down. Hey, that's weird. What's the base on that logarithm? They didn't tell me. Because it's a 10, it's a common log, so put a 10 there if it bothers you. But 10 to the log base 10 of 13, 10 to the log base 10, those are going to knock each other out, and you get a 13. So like a whole page of those on your test would be good? Yeah. No, we're not going to get that. All right, number 1 is still on your paper here. So log base 7, 7. I know they cancel. And usually we had something up here in the exponent. Guys, I claim you do have an exponent. What do you have? You always have a 1. So the 1's going to drop down, you get a 1. Technically, that is also one of the properties of logarithms where it said if the bases match, that your answer comes out to 1. But you don't really have to have the properties memorized for those if you understand how the inverse properties work. So here, what base is this logarithm? It's a common log, so secretly there's a 10 there. So 10 to the log base 10 cancel, 5x drops down, that's awesome. Oh my gosh, this is getting boring. The 3's log base 3 will cancel, the answer's 2. It's got to be more tricky than this. Oh, look at number 4. Do they match? They don't match. So you have a choice. You could either look to make them match, or you could just rewrite it. So one way to answer this question is to rewrite 36 so that it is a 6. What's another way of saying 36 as a 6? 6 squared. So now the bases match, and I can clearly see that the 2's just going to drop down. But the other way to do this question is to go back to that rewriting formula. You can say 6 to what mystery power is going to give you 36, and then you think for like 2.5 seconds, and you go, the answer is 2. So I don't care which way, technically they mean the same thing in math, because the property is derived from another property, so they all kind of tie together. On your test, when it says to do something to rewrite the question, I need you to show me something. So whether it's rewriting as an exponential or whether it's rewriting so the base is different, you need to show me some work, because we are not going to limit you with a no calculator part of the test this time. And guys, we are very well aware of the change of base on your calculator. We don't want you using it. We want you to be able to show us the other way, okay? All right, number 5. Log base 3 of 1 over 81. So your choice. You can either rewrite it as an exponential, or you can rewrite it so they have matching bases. So, I don't care. Rewriting as an exponential would be 3 to what mystery power gives you 1 over 81. If you rewrote it with matching bases, can anyone think of a way to rewrite 1 over 81 as a base 3? That's kind of confusing. So how would you take 1 over 81? First of all, you got to flip it, and then you got to change a 3 to an 81. -4, very good. So either way, guys, you're going to have to think about the fraction component to it. This isn't like a big mystery. The answer is -4, clearly. And then number 6 is nice, because I noticed we have the inverse property again. E to the natural log, they're going to cancel. X squared drops down. So if I was a student in PreCalc right now, when I do my homework tonight, because that second homework assignment is all this stuff, I would work really, really hard to not touch my calculator so that way I'm ready for my testing. All right, we have more practice that we can go through. I'll do the fun ones, huh? This is not on your worksheet anywhere. 8 to what mystery power? It's going to give you 512. That might need a chart. Look on your chart. Is it 3? I think it's 3, yeah. That one's boring. We'll skip it. Let's look at 1C. It says log base 2 of 1 over 32. So again, two choices. You can either rewrite it. 2 to what mystery power gives you a 1 over 32. Or you could try rewriting 1 over 32 as a base 2. They mean the same thing technically, guys. So think about going from an integer to a fraction. What's going to have to be true about your power? It's going to have to be negative. How do you change a 2 to a 32? Yeah, fifth it. Okay, there we go. -5. Oh boy, here's a challenging question. Take a look at this one. 16, some mystery power, has to equal the square root of 2. Now right away I can already tell you I don't like square root of 2. I'm going to rewrite that as 2 to the 1/2. That is a thinker, especially without a calculator. So when I get stuck on a question where I can't use a calculator, and this is a really good SAT question, by the way, and it's a really good SAT question for the no calculator gridded response part. This would be perfect for that question, that test. You can't really compare 16 to 2 easily in your brain. So what if we could rewrite a 16 as a 2? So like, what's another way of saying 16 but as a base 2? 2 to what power? 4? So you have 2 to the 4th instead of 16, raised to some mystery power, has to be the same thing as 2 to the 1/2 power. Okay, guys, in math, we don't usually use question marks for things that we don't know. What do we usually use in place of a question mark? We usually use X. I purposely don't like X's on these problems because sometimes there are X's in the problem and then it gets really confusing. So for now, I'll change it to an X, guys. 4 times X is the exponent here. So you have 2 to the 4x is supposed to be the same thing as 2 to the 1/2 power. Well, think about logical math here, guys. That means 4x equals 1/2. Solve that for me, and be careful, PreCalc, because you'd be surprised how many kids are going to get this wrong. 4x equals 1/2. What happens when you divide by 4? What is 1/2 divided by 4? 1/8. 1/8. Because you'd multiply it by 1/4. Okay. The answer is 1/8. Took a lot of mental muscle to get there, though, guys. Those are the kind of questions where you really have to understand your properties, because it is I can't predict what's going to be on your SAT test, but like the people who write the SAT math test are math teachers like me who are evil, and they're looking for questions that will display someone's knowledge of a concept and in a way where a kid who doesn't know what they're doing is not going to get it right. So you're supposed to be the kids who do know what you're doing, and you have to get it right. Got it? All right, take a look at this question. This is on your notes. Financial literacy. So there's a formula hidden in here. There's the whole formula. And it's a derivation of a formula that you guys have, but they've already taken the liberty of like rearranging it and using log properties to expand it so it's in a user-friendly notation for this problem. So Ms. De Silva has $3,000 to invest, and she would like to invest into an account that pays continuously at 6%, and then use that formula where A is the current balance, P is the original principal, R is the rate as a decimal, and T is the time in years. So the formula starts off with natural log of A. So they call it the current balance. What they mean by that is like the final balance, because like at that moment in time that is your balance. So she wants $6,000 after so much time goes by. So that's $6,000 right here. Minus, and then we have the natural log of her original principal, which was $3,000. And it equals the interest rate, which is 0.06, because you got to write it as a decimal. And then times how many years. But that's the question. We don't know how many years, so just call it T. And I know this left side of the equation is like a hot mess, but the right side of the equation you're supposed to solve for T. So all you need to do is divide by 0.06. So on your calculator, whoops. Either hit enter or use parentheses before you divide by 0.06 and tell me how much time this woman's going to have to leave her money in the bank account for. To the tens place, please. Heard 11.6. All right, 11.6 years. Tomorrow, I think, oh, I'm sorry, not tomorrow. Next week sometime, early on next week, we're going to be starting a section on finance. We're going to use our app on our calculator. We're going to do more realistic real-life questions, because let's be honest, these questions are pretty lame. Like, people don't usually have... Well, first of all, you're not going to find an interest rate of 6%. That's the first issue. Most people don't let their money sit still for 11.6 years either. If you're just letting it sit in a savings account, that's kind of weird. So we're going to have more realistic questions coming up. Is this not right? Are we okay? Oh, okay. All right, seismology. All right, I am not a seismologist, but apparently we did some Googling first hour and found out something about the Richter scale, so we'll talk about that. Anyways, Richter scale measures the magnitude of an earthquake. We don't get too many earthquakes here, but we do have a fault line kind of near us. Anyone ever felt that little minor earthquake we got a couple years ago? I sleep through them every time. I don't know. Anywho, that's the formula. I'm guessing someone named Richter, derived this formula that calculates the power of the earthquake. So the E, the variable in that formula, represents the energy that is released by the earthquake in kilowatt hours, and that's measured by, I think they're called seismographs, but you've seen those things with the needles and they like bounce back and forth, and then they can measure the magnitude of the wave. Okay, so that's what they're measuring, is how powerful the wave was from the earthquake. Now, be careful, this time the million is actually part of the number. It's not part of the variable labeling anywhere in here. So E is 1,000,000 kilowatt hours, so you're going to need to plug in 1,000,000 into, boop, right there. So, on your calculator, 0.67, and what kind of log is this? That's the common log, so use the right button. Common log of 0.37 times 1,000,000. Close that parenthesis to stop the logarithm function, and then add 1.46. I think it's 5.2. I didn't write it down last hour, but that's, I think, my memory. Okay. So, on the Richter scale, this earthquake scored a 5.2. Now, me not really understanding earthquakes, I don't really know what that means. But since we did a little Googling last hour, we found out that earthquake scale goes up to 9, basically. And here's the reason why, guys. Now, this is kind of confusing at first, but we've talked about inherent domains on our applications before, where like the medicine question, where I forgot what question it was, but like we said, the domain is really on the function itself, it's infinity, but like in real life things don't go on for infinity, so there's an inherent domain. So this one actually has an inherent range. If you were to graph the logarithm function, I don't know exactly what it looks like, but let's pretend it looks kind of like this. So this piece of the logarithm function has a range of negative infinity up to positive infinity. It goes up forever. But the magnitude for the Richter scale does not go up forever. It kind of stops at 9. And that's because I had a friend look this up. She found out, well, think about how this grows, guys, really slowly, right? If you're measuring how much energy the Earth is putting out from the sliding plates, as you get farther along your domain, you're talking about a lot of energy. Like, they equated it to TNT. So if you have an earthquake of a Richter scale score of 9, it's a lot of TNT. Like, you'll feel it very far away from the earthquake's epicenter. But if you want to look at the Richter scale and figure out how something can score a 12, you're going to find out that the amount of TNT that's needed to produce that magnitude would explode your planet. So you're not going to see an earthquake that goes off of the Richter scale because we wouldn't be here to measure it, I guess would be my point. So there's an inherent range this time, even though technically the logarithm graph goes up forever. Not really, because your Earth could not produce that much kilowatt hours without having some major bad things happen. Alright, that was fun times. Story time with a Bruzo. Alright, I'm going to stop the video.